Hi, today we are going to look at section 2.7 in Algebra 2, and you can see that the objective for today is that I can solve linear quadratic systems. As a little bit of an introduction, I'm going to have you think about a situation where you can graph both a line and a quadratic or a parabola in the same grid. So you can see here, I want you to make a grid and then graph a parabola, and then draw a line anywhere you want. Okay, for me, I chose to draw it right here. Question A says, count the number of points of intersection. Okay, so when I look at the line and the parabola, I see that this is the first point where they intersect, and then there's another one here. So there are actually 2 points where this line and parabola cross. Part B says, okay, now we're going to sketch another parabola in a coordinate plane. Okay, so I'm going to graph that. In this case, it wants me to explore different ways that they can intersect. Okay, so we just said, yep, we could draw it right here, and it goes through in 2 spots. But I want you to think about it and see if you could draw lines in other places and end up with different numbers of points of intersection. Hopefully, as you thought about it, you saw that maybe if you drew a line way down here, there would be 0 points where it intersects. And the other option would be, isn't it true that if we had a line that just kind of slightly grazed the side of the parabola, that it would actually only intersect at 1 point? So this little introduction just shows this idea that if I am graphing a quadratic or parabola and a line in the same coordinate grid, I could end up with 3 different scenarios. A situation where they cross in 2 points, 1 point, or 0 points. This next slide is going to take this idea, but we're going to actually apply actual values and numbers to it. Okay, so it says how many real solutions does the system have? We're going to do it graphically. Now, when we're doing things graphically by hand with these more complex systems, you're not going to find the actual systems by hand graphically. We're going to use our calculator later for that. For now, we're just getting the general idea. If I have y equals x squared, remember, I can make an xy chart. If I plug in 0, 0 squared is 0. That's the vertex. I could have seen that without even plugging it in. But remember, I always have the option to figure out my next point by plugging in 1. Well, 1 squared is 1, which means it has a point at 1, 1. Now remember, a quadratic is symmetric, so if there's a point at 1, 1, there's also a point at negative 1, 1. I could also plug in 2. 2 squared is 4. So I could go over 2, up 4, which means I'd go back to up 4. So this purple graph, a little shaky there. This purple graph is my parabola. Now on the same grid, I can graph y equals 2x, which is linear. Technically, it's 2x plus 0. Remember, this is my b value, which is my y-intercept. So this graph has a point at 0, 0. And then the thing attached to the x is my slope. And since it's 2, it's like a 2 over 1, which means from the green point that I already plotted, I'd rise 2, run 1, rise 2, run 1. If I graph that line, I can see that this is a situation where we have 2 solutions because there are 2 points of intersection. Okay, so those points of intersection are the number of solutions. Now this was a fairly basic graph, so I could actually see that those points are at 0, 0 and 2, 4. But that's very rare that I can graph these by hand that nicely and get the answers. The second question says, how does modifying the linear function in the system change the number of solutions? So you can see we're going to add b. So this time I'm going to graph my parabola y equals x squared in green. We already went through how to graph that, so I'm just going to replot it. Then it goes through that point. Now I once again could, touchscreen's on. I once again could graph just 2x, which is the one we just graphed. And we saw that in fact 2x is just 2 points, 2 solutions. That's what we already did. Having said that, what if I start changing that b value? What if I decided to graph y equals 2x minus 6? 2, 3, 4, 5, 6. Rise 2, run 1. It would look like this. That would be a case where we'd have no solutions because they never cross. And then we can look at this. If I decided to graph y equals 2x minus 1, I would graph a point at -1, and then I would rise 2, run 1, and this is that case where we can see that it slightly brushes the edge of that parabola, and that's where we end up with one solution. Okay, so these are the 3 different cases with more numbers. We saw it in the warm-up and we see it here. I want you to take a second and try an example like this, where it says, determine just the number of real solutions of the system. Okay, so solve graphically, you're just figuring out how many solutions, not what they are. So pause the video, graph both of these in the same grid and see what you get. Again, if I'm going to make my xy table for 3x squared, 3 times 0 is 0. I plug in 1, 1 squared is 1 times 3 is 3. So I have a point at 1, 3, negative 1, 3. If you plugged in 2, 2 squared is 4 times 3 is 12. That's way up there. So we should have been able to see that it's a graph that looks something like this. Now, when I go to graph the line, my y-intercept is at -2, and my slope is 3, which is 3 over 1. So I'd rise 1, 2, 3 over 1. Now remember, this point is at 1, 3, so 1, 1 is going to in fact be below that. This is my line. It's very, very close, but these would never cross, so there's no solution. Okay, so you do need to be able to sketch some very basic parabolas by hand and a line in the same grid to be able to determine the number of solutions. And once again, it is solely based on the number of times those graphs cross. The next thing we want to be able to do from today is to find more exact solutions. And we can do that algebraically by using the idea of substitution. You've done this before with linear systems where you have 2 linear equations, and now it's just a little more complex. The idea of substitution means that if I know y is equal to 3x squared plus 3x minus 5, I am allowed to substitute that for this y in the other equation. I do recommend taking the quadratic part and substituting it into the linear. Sometimes it's just a little bit easier. The 2x just stays, so I'm going to do 2x minus. Make sure you put your quadratic in parentheses. So I'm going to replace that y with 3x squared plus 3x minus 5. And it's all just equal to 3. Okay, so this stays, and I replace the middle. Now, I have to put it in parentheses, especially if there's a minus, because I get 2x minus 3x squared minus 3x. A negative times a negative is positive. Plus 3. Now, I want to get everything on the same side and combine like terms, so I can subtract 3. I have negative 3x squared. 2x minus 3x is minus 1x plus 2. Here's the problem, though. I want to solve this quadratic now, and that's why it falls in this chapter, because we learned how to solve quadratics. First, we learned how to solve by factoring. Second, we learned how to solve by using the quadratic formula. You could use the quadratic formula as is on this problem right now, but just so you know, I'm going to try factoring because it is quicker if you understand how to do it. The only problem is with factoring, I strongly encourage you to have a positive a. I wouldn't need to show this work, but if I want to make this -3 positive, I would move it to the other side and add 3. But really, you're just flipping every sign. So you wouldn't have to show the work that I just showed, but you could go through and just change all the signs because you'd just be moving it to the other side. Now, this is a case where my a is not 1, so when I set up my table, I have to multiply to get to a -6, because 3 times -2 is -6, and I'm going to add to get to a 1, that middle number. Well, I immediately, and again, the more you practice this, the quicker you're going to get. I know to get -6 to multiply and add to a 1, I'm going to use the 2 and 3 because they're 1 apart. Multiply to a negative, one number has to be negative, one has to be positive, and since I'm adding to a positive, it's a positive. 3 and a -2. Now really what we've done, I'm going to move back up here, we have decided that we can break this x piece apart into -2x and 3x. That's what this tells me. We did use the tool of the box then. We said, okay, let's put the 3x squared in the upper left. These 2 new pieces go along the diagonal. And then finally the -2 goes here. This is just a tool for me to have a visual. Now I take the greatest common factor out of every row and every column. So if I look at the top row, 3x squared and 3x, they have a 3x in common. Negative 2x, negative 2 are both divisible by negative 2. 3x squared and 2x is just an x, and 3x and negative 2 is just a 1, which means that this factors as 3x minus 2 times x plus 1. Last but not least, remember when we're solving a quadratic by factoring, we take each factor and figure out when they're equal to 0. 2, x equals 2, divided by 3, x equals 2/3, and this one I would just subtract 1. X equals negative 1. So these are the two solutions that would work in both of those equations. Having said that, because the equations have y's and x's in them, I actually need to write these as ordered pairs, so I probably shouldn't have circled this yet. In order to figure out what the y value is, I need to take one of the equations. I'm going to take the linear one. Okay, so I'm running out of space here. So we're going to find ordered pairs. Okay, so I'm going to take the 2x minus y equals 3, and my first x was 2/3. So I do 2 times 2/3 minus y needs to equal 3. 2 times 2/3 is 4/3 minus y. Since it's thirds, I'm going to change 3 to 9/3. Subtract 4/3 from both sides, I would get 5/3, right? So if I subtract 4/3, 9/3 minus 4/3 is 5/3, and I would have to divide by a negative 1. So I get y equals negative 5/3, which means the ordered pair was that when the x is 2/3, the y is negative 5/3. Again, the reason I need to get both the x and the y ordered pairs because the equation or the system has x's and y's in it. Then I would have to take 2x minus y equals 3, and once again, plug in the negative 1 for x. So 2 times negative 1 minus y equals 3. This one's a little easier, no fractions. Negative 2 minus y equals 3. I'd add 2, negative y equals 5, divided by negative 1. I get y equals negative 5. Okay, so now I have the ordered pair. I plugged in the negative 1. I got negative 5. So these are my two solutions. Okay, so you do have to take that extra step and find the ordered pair. Now, when I went to factor, I forgot to mention that I do need to first check to see if there's a greatest common factor. 3, 1, and negative 2. There was not, so I didn't have to factor that out. All right, let's try another one together. Okay, so we're going to try number 1 together. Once again, I'm going to substitute this quadratic for the y. So I have 2x minus 2x squared minus 6x minus 8 should equal 16. Distribute. Get 2x minus 2x squared plus 6x, because a negative times a negative, plus 8 equals 16. And again, I'll subtract 16 from both sides. Combine these, so I have negative 2x squared plus 8x minus 8 equals 0. Again, if I'm going to factor, I need this to be positive. So if I move it all the other side, I get positive 2x squared minus 8x plus 8. Okay, so remember, when we shift it over, all three signs change. Now again, I'm going to try to use factoring, but what I notice is that the 2 and both 8s are all divisible by 2, which means my first step is to factor out a 2. So this is the same as 2 times x squared minus 8 divided by 2 is 4x plus 8 divided by 2 is 4. And the reason that's nice is because now to factor this, a is 1, so I just multiply to get to 4 and add to get to negative 4, which means it's negative 2, negative 2. And when we do it this way, we get to just rewrite it right away as these as my factors. 2 times x minus 2 times x minus 2 equals 0. Now remember, we take each factor. When does 2 equals 0, x minus 2 equals 0, x minus 2 equals 0. But if it's just a number, there's no x to solve for. And both of these give me x equals 2. Sometimes we have a repeated solution like that. That's when we're only going to have one answer. Don't forget, take that equation, 2x minus y equals 16. I prefer to take the the linear, sorry. Plug 2 in for x, so 2 times 2 minus y equals 16. 4 minus y equals 16, subtract 4, negative y equals 12, divide by negative 1. Y is negative 12. So my one solution in this case is the ordered pair 2, -12. All right, go ahead and pause the video and try number 2 on your own. Okay, when you do this one, hopefully you got 4x minus -3x² plus x plus 4 is 2. When you distributed and solved, I'm hoping you got to the point where you got positive 3x² plus 3x minus 6 equals 0. If you didn't get to that point, make sure you go back and double check your work in these first few steps. I didn't show it, so double check your negatives. Now I see that all 3 of these are divisible by 3, so I change it to 3 times x² plus 1x minus 2 equals 0. And then when you went to factor this, you should have had 3 times x minus, or x plus 2 times x minus 1 equals 0. Okay, so when you went to factor, that's what you should have had. Set each factor equal to 0. Again, you don't always have to show all this work. This doesn't work. I get x equals -2, x equals 1. So this is going to be a case where I have 2 solutions. We'll take 4x minus y equals 2. 4 times -2 minus y equals 2. -8 minus y equals 2. -y equals 10. Y equals -10. So my first solution would be the ordered pair -2, -10. And then when you plug in the 1 for x, 2, -y equals 2, then y equals +2. You should have the ordered pair 1, 2. So these were the 2 answers you should have come up with. All right. Before we sign off here, I want to show you this last example. And we're not going to answer the second part. We're not going to worry about that. But it says Andrew kicks a ball up a hill for his dog, Laika, to chase. The hill is modeled by a line through the origin. The path of the ball is modeled by the quadratic function. Okay, so this is the ball, and this is the hill. Okay. How far does the ball travel horizontally? Okay, so if we want to know how far the ball travels horizontally before it hits the hill, we're looking for this point, which means we are taking, and you can see they give us the equations right here. We are taking these 2 equations and we are solving them, solving the system. So we're making that a system, -0.5x² plus 6x, and y equals 0.5x. And like I said, if you have something like this where you want an exact value, we could use substitution. But in this case, we're actually going to use our graphing calculator. So I'm probably not going to come back to this slide. But what I'm looking for, because my answer is how far does it travel horizontally, that's the x value. So I want the x value for the second point of intersection. Okay, so I'm going to go to my graphing calculator in just a second. But again, I want the x value for the second point of intersection. That's what I'm looking for. So now I'm going to go to my calculator and show you how you can graph a system like this. Okay. As a reminder, your calculator, we can find on Schoology if you're in my class. If you don't have one, I do continue to strongly encourage you to find one that you can use, because it is always easier to do this by hand. Okay, so you guys are Algebra 2, but it's the same calculator. Find that on your website. Go to Start, click up here. And last but not least, to graph, you go to the y equals button. I'm going to type in both equations. Negative, remember you have to pull that off of here. 0.5, the x also has to come off of here. I'm just typing everything on the calculator rather than my screen so I don't make that mistake again. Plus 6 times x, that's my first one. Hit enter. And the second one is 0.5x. That's the linear one. Okay, I go to graph it. I see what I see. And the problem is right now it looks like a line and a line. And I know that's not what it should be. It should be a parabola, which means my window isn't big enough. Eventually we'll learn how to think about it holistically and change it by hand. But for right now, you can probably get away with understanding the zoom button. If you go to zoom and you want to see more, you go to zoom out. Number 3, hit enter. You'll see nothing happen, but there's a cursor there. If I hit enter again, now I can see a better picture. So that's the quickest way. Now sometimes it doesn't give you a great picture. We'll talk about what you can do in that case. Now I want this second point of intersection. That's what we decided, the y value of that. So I go second, calculate, and number 5 helps me find intersection points. Enter. Now if I start saying, yes, this is my first curve, second curve, they're going to give me this first point of intersection. So to find this one over here that I want, I need the arrow key to the right until it gets close. And then once I'm close to that one, I hit enter. Yes, it's on the first curve. Enter, yes. Guess, yes. And you can see that it is 11. So we don't care about the y value. We care about the fact that it is an 11-foot horizontal distance that it travels. So my answer for that question would have been 11 feet. Now last, before I sign off, I do want to make sure you know how to change your window back, because if I go to graph anything else, it's going to keep it like this. If I don't like this picture anymore, if it gave me something that doesn't work, go back to zoom. Number 6, Z standard, that's the standard viewing window. So anytime you change or zoom in or zoom out, to get back to normal, just go back to zoom and go zoom standard. All right, that's the lesson for today. You can go ahead and sign off and work on your 2-7 day 1 Pearson practice. Thanks.